going to be learning about the science of NFL football. So we're going to take those laws that we worked on Wednesday, and we're going to apply them to football. So I hope that you guys are ready. We're going to watch a couple of videos about football, and then we are going to be answering some questions on a worksheet that goes along with this. So that looks like this, and what you want to have in front of you right now. And this is the worksheet. Bryson, I'm sorry you aren't playing flag football anymore. I can't imagine your mom taking away your phone right now. Oh no. All right. Well, it's really kind of a bummer that we can't be playing our sports right now. So we'll learn about it, and one day soon we'll be back out there playing. And then you can think about physics as you collide with one another or grab their flag. Okay, so this is the worksheet that you should have in front of you right now. It's posted on Edsby on Sunday. It is not going to be a very difficult one to handle. There's only 9 questions on it, and I'm going to help you through it. So you get a benefit of getting me walking you through this by showing up for class today. Our objective is that you're going to be able to explain all 3 of Newton's laws, and you'll be able to do this through football examples. So you're going to get lots of examples of this, and then we're going to check and see if you understood and can maybe use your own words to explain these laws. So things that were recently due. All right. Oh, we're not on the slide. We got to go back to that. Okay. So back to our slide here. We have some things that were recently due, and that is Newton's Laws notes that we did together on Wednesday. Those were due right before class, so hopefully you got those in the submit box before you showed up to class today, because they were due at 11 a.m., which was 8 minutes ago. Your My Workout Speed and Acceleration assignment was due on Tuesday earlier this week at noon. We did that together last, I think it was Thursday, last class of last week. We did that together in class. Some of you came to my office hours to get help with that, and those that did, I think, got really good scores on those assignments and understood it, and those that did not do so well. So check Edsby grade. Those are mostly graded. There might be 1 or 2 left, but you should not see, if you see an overdue reminder for anything right now, it means you have not submitted it. If you have submitted it and I don't have it graded yet, it will at least say that it was submitted either on time or late, but it will not show overdue. So if it does show overdue, it means you haven't turned it in. All right, so somebody else, Theo's coming to join us. Good morning, Theo. Welcome. Glad you could join us on this fine, rainy Friday morning. All right, so we were just talking about what was due. So Theo, hopefully you got your things in. Science of NFL is what we're doing today. There is a worksheet that you have gathered, and it looks like this. You want to have this handy. So Theo, I know you've had some trouble downloading the stuff, so hopefully you were able to get this ahead of time and have it ready right now. Okay, going back just momentarily to our slide to finish up what we're going to talk about, and then we'll get started. Okay, so next week we are going to start doing a series of labs and challenges, competitions, and I am hoping to culminate all of this in the last week of school. We're going to have a little physics Olympics. And since we can't get together to do this, I'm actually going to make this extra credit. So I have some availability for extra credit here for participating and explaining things through Newton's laws with these challenges. So on Sunday, I'm going to put up a materials list that you want to check out. I know there's going to be a lot of materials that you'll want to have for these next couple of weeks, and you might not have all of them. And that's okay. So I'm going to give you some ways to improvise. And if you cannot get the materials, then you can't get the materials, and it's going to be okay. You won't be penalized in your grade for not having those things. But what I'm hoping for is that you can join me. I'm going to be doing the labs and activities right with you live on Zoom in our classes. And if you can do them with me, fantastic. And it'll be a lot more fun. If you cannot, then you will just watch me do it, and you'll be able to gather my data and be able to do the lab just the same. And if you miss Zoom class, then you're gonna check it out on the YouTube video and fill in your lab sheet that way. So be looking for that stuff. I'll be posting it on Sunday, probably afternoon or early evening, and you'll know what you wanna try to gather, okay? All right, we're gonna go ahead and get started then. Before we do, is there anybody that has any questions about things that are due, coming up? Oh, by the way, today's assignment is due on Monday, right before class. Actually, I don't have class on this Monday. It's going to be Tuesday. So it's still going to be due, though, on Monday at 11 a.m. Because that is what I told you at the beginning of the week. So we're going to stick with that. But next, well, yeah, we're going to stick with that. Okay, so any questions? See any hands up? All right, we're gonna go ahead and get started then. And you have, of course, this sheet right here. And let's take a look at what we're looking for in our first video. There's 4 questions we're gonna be answering. And the first question is, really basically you're going to be kind of finishing the sentence. In football, we see unbalanced forces. When one player exerts an unbalanced force, hits another player and causes the player to do what? So that's what we're going to be looking for. And then we will be, and I will pause at that point and we'll discuss it. So I'm going to help you. And then in the next question, we're going to be looking for a vocabulary word. We learned it in our notes earlier in the week. It is a definition for a player's natural resistance to an unbalanced force. It means that, you know, the player wants to keep on doing whatever it's doing. It's going to resist any change. Okay, and then how are mass and weight different? We've talked about that in class several times. Probably already know that answer. And if a player has more mass, they will also have more what? All right, that's our preview. That's what we're looking for. And we're getting started right now with this first video. All right. Hopefully you'll be able to hear and see this and it won't buffer for us.
Whether it's a running back breaking through the secondary or a wide receiver on a foot race for the end zone, most offensive players in the NFL.
I'm pausing for just a second, wanting to make sure that we are all actually seeing this video. Can you guys show me a thumbs up if you can see this video and you were hearing the very beginnings of it? And let me play just another second. So
I'll have a single goal in mind to get.
Okay, are you hearing it? Looking like it. Okay, thank you guys very much. You can put your thumbs down. And somebody wants to say something. Okay, all right, here we go.
Get downfield as far and as fast as possible.
We're thinking, wow, I've got to get from A to B within a certain time frame, and I can't let this guy throw me off track. So it's kind of like a chess match at that point in time. It's the battle to see who's the toughest.
Defenders, on the other hand, have a different goal: to stand in the way of the offensive player and stop his forward progress.
When you're coming in and making that tackle, you've got to come in and you've got to stop him right there on the dime.
Who wins this epic battle between the ball carrier and the defender? Newton's first law of motion helps supply some answers.
Newton's first law says that if an object is at rest, it requires an unbalanced force to make it not be at rest. Or similarly, if an object is in motion, it tends to stay in motion in a straight line at a constant velocity unless an unbalanced force acts on it.
In football, we see unbalanced.
I'm going to pause for a quick second here because this is where the answer is coming, so get ready to write.
Forces whenever one player exerts a force on another and causes him to change his direction and or speed.
All right, I'm going to play that again in case you missed it.
An unbalanced force acts on it.
In football, we see unbalanced forces whenever one player exerts a force on another and causes him to change his direction and or speed.
Okay, so who can tell me what goes there? So if one player hits another player, what does that unbalanced force of the hit cause the player to do? I saw somebody raise their hand. It's Trevor. All right, Trevor. What do you think?
Change direction and or speed.
Yes, change direction and or speed. Excellent. Go out for a pass. Okay. So let's keep on going.
Imagine that a quarterback is just taking a snap from the center, and a lineman gets free from the opposing team and is coming from the other side, and when they collide, you could see an unbalanced force acting on the quarterback, driving him across the field in the direction of the charging lineman. That's about as unbalanced as it gets.
In physics,
all right, get ready. Here comes answer number 2.
a player's natural resistance to that unbalanced force is something called inertia.
Right, that goes in the blank right there. We learned about inertia. This is Newton's first law. We learned about this on Wednesday. So listen to what it is and then how it applies.
On a football field, you can think about inertia as being a running back who's already in motion, doesn't want to change the fact that it's already in motion. So it's going to take some external unbalanced force, i.e. a defensive player, to stop that running back.
Consider former New Orleans Saints running back Deuce McAllister, who at 6'1", 231 pounds, used his inertia when running to make him hard to tackle.
The size of the player is important to the concept of inertia because higher mass means more inertia.
But a player's mass is different from his weight.
All right, get ready for number 3.
Mass is a measure of how much matter an object has, while weight is a measure of how strongly an object's mass is attracted by gravity.
Okay, I am gonna call on somebody here to explain to us the difference between mass and weight. This is a concept that we have looked at in two different topics or 2 different classes in the past. So, all right, Trevor's got his hand up again. That's so awesome, Trevor. All right. Oh, let me see if there's anybody else that wants to answer. No? Okay. All right, Trevor, what's the difference between mass and weight? Can you tell us first what is mass?
Mass is a measure. Mass is the measure in
well, I'm going to let you answer it the way you wanted to answer it. So how are mass and weight different? I think you had a plan for that answer.
Yeah. Mass is a measure in matter.
How much matter? Exactly. It's a measure of how much matter is in something.
Right. And gravity is the measure in not gravity. Weight is a measure in gravity.
Yes, exactly. Right. So mass is a measurement of how much matter is in an object. And weight is a measure of how strong the force of gravity is pulling on that object. So weight has to do with gravity, which can change depending on your location. If you are, say, on Jupiter, on a planet that is much more massive, you're going to weigh more. Versus on the moon that is much smaller, you would have a lower weight, but your mass would be the same. Okay, thank you, Trevor. Okay, so going back to, we just have one more question to answer here.
So for example, a body on Earth would have the same mass as that body on the moon, but it would weigh less on the moon because gravity is less on the moon than it is on Earth.
He just copied what I said.
NFL players with more mass have more inertia and are harder.
I forgot to warn you that was coming up so quick. Okay, that's the fourth question. If a player has more mass, they will also have more weight
than it is on Earth.
NFL players with more mass have more inertia and are harder to move off their path. This concept even works on a quarterback sneak, when a quarterback uses the combined mass of his entire offensive line to gain a yard or two.
If you've got an offensive line that can overpower the defensive line, that's just what you do. You get on their hip and you just fall, and you just ride that wave forward.
In the NFL, whenever players go head-to-head, it's Newton's first law of motion that helps determine who will win the battle of the gridiron.
All right, so there you have it. That is Newton's first law of motion. And in this law, this is also called the law of inertia. So in Newton's first law of inertia, it says that an object wants to keep on doing or stay in the same motion that it's in. So if an object is in motion, it wants to stay in motion, but not just any old motion, it wants to stay in the same motion. So if it's directed northward, it's going to stay going northward in a straight line at that same speed. It's not going to speed up. It's not going to slow down. It's just going to keep on going. If I was throwing this football and we were in space, like it suggests behind me, and there was no air particles to be, to slow this football down, being an unbalanced force that would eventually cause the velocity of this football to change. If there was no force doing that, no unbalanced force, this football would just keep on going forever and ever and ever and ever. As you can see, this football has been pretty worn. Maybe a past dog got to it once or twice. Okay. All right. So we're getting ready to go to Newton's second law, how we are going to describe that, and how football plays into Newton's second law. And remember, we were talking in the beginning today about Newton's second law being the one law that has a mathematical equation. And in that law, we are calculating the force of an object. And by doing so, what are the two things that we multiply together to equal the force of an object? So actually, let me back up for a second. Going back to Newton's first law for a minute. Remember, we were talking that an object that is in motion wants to stay in motion, or if the object is just at rest, it wants to stay at rest, unless an unbalanced force acts on it to change it. So in the second law, Newton's explaining how, or what happens when an unbalanced force does act on it. So if there's no unbalanced force, it keeps on doing what it's doing. If there is an unbalanced force, then that is equal to the product of what two things? So the properties of an object, what two properties do you multiply together to get the force in Newton's second law? Anybody got this? It was the question I asked in the beginning of class and nobody seemed to know, but maybe you didn't have your notes out from yesterday. I do hope that notes are supposed to be useful. Like, you're not going to learn everything just by writing it down one time. You do need to review them, have them handy in the next class, because I'm going to ask you questions about it. So in order for you to get this, you are going to have to keep reviewing it. And the next several weeks, you're going to be applying Newton's laws to everything, and you're going to need to be able to explain them. So force equals mass times acceleration is Newton's second law, which is also called the law of acceleration. All right, so we are now looking at questions 5, 6, and 7 on our sheet. So we just did 1 through 4. And we are now just going to answer 2 questions in the next video, 5 and 6. We're looking for the formula for Newton's second law. I just finished saying it. So if you didn't catch it, you will catch it on the video. And then impulse. There is a vocabulary word we learned on Wednesday that impulse and this word are really pretty similar. Impulse is just the change in this word. So we're going to learn what that is. And by the way, to give you a hint on what it is the force of a moving object. So imagine a football player running at high speed and tackling you. He's got a lot of blank besides inertia. Yes, that's right, Theo. It is correct. Mass times acceleration. Yes, good job. Okay, here we go. We're going to look at Newton's second law. Somewhere. Here it is.
To be an NFL kicker takes more than just nerves of steel and a strong leg. It also requires help from one of the key laws of physics.
It's easy to say, well, I just kicked the ball. Well, let's delve into it. Let's look at the specifics. What actually happens when you kick the ball, and why does the ball go where you ask it to go? And it is Newton's second law of motion.
The second law is one of 3 laws described in 1687 by Sir Isaac Newton, who used them to describe how and why objects move.
So the second law says if you have an object with a mass that is accelerating, and acceleration means a change in velocity, that is equal to the amount of force applied to the object. The way we say it with words is F is equal ma.
This also means that in order for an object like a football to accelerate, a force must be applied. To illustrate Newton's second law in kicking, we asked Morton Anderson, the NFL's Newton's second law in kicking to accelerate.
Sorry, I was trying to stop it right here. All right. So the big F there stands for a fart. No, force. Okay. And M for mass and A for acceleration, and they are right next to one another, which means you multiply mass times acceleration. All right, that's number 5. One more question on this, and it comes up in about 2 minutes.
Right, a force must be applied. To illustrate Newton's second law in kicking, we asked Morton Anderson, the NFL's all-time scoring leader, to perform his craft in front of a high-speed phantom camera. The entire procedure unfolds in less than a second and a half, from snap to hold to kick.
It's all about training and rehearsing and doing something over and over and over again.
To reduce the chance of a block, NFL kickers take just 3 steps to the ball. The final step is with the plant foot, which provides the stable platform for the kick.
I call it the moment of truth, and the moment of truth is basically when your plant foot hits the ground next to the ball. You're either in the right position or the wrong position.
The kick itself involves the entire leg building the force necessary to launch the football.
It's a hammer, and you're swinging the hammer, and you're trusting it, and it's going to be, it's going to be impacting the ball with great velocity.
An NFL kicker's foot is in contact with the ball for just 8 1/1000ths of a second, and in that time, his foot applies up to a ton of force to the ball. This quick, violent strike is a perfect example of what's known in physics as an impulse.
Impulse is an important concept.
Get ready. Here it comes, number 6.
because there is a finite time over which the foot is in contact with the ball, and during that time there's a force applied to the football.
An impulse is equal to the force multiplied by the time the force is applied, represented by delta T. If force is graphed versus time, it's possible to see how a larger force or a longer time for the force supplies a bigger impulse.
Since impulse is really just the change in momentum.
Did you catch that? That's your answer. Impulse is really just the change in...
Supplies a bigger impulse.
Since impulse is really just the change in momentum, and since a ball doesn't change its mass, we're really just talking about the change in the speed. The bigger the impulse, the bigger the change in speed, which means the faster the ball is moving after it leaves the kicker's foot.
Ironically, Anderson says the distance of the field goal doesn't change his approach to the kick itself.
Mentally, you want to look at a 50-plus yarder, like a 40-some yarder, with some room to spare. I think that's a good way to kind of fool yourself into thinking it's a shorter kick.
Whether the kick is short or long, Newton's second law explains what an NFL kicker must do to send a football through the uprights.
Okay. All right, so here you have, let's stop this for a second. So yeah, here you have in football, Newton's second law saying that essentially the more force that you, or I'm sorry, let me start here again. So if the football, let's say, was larger and had more mass to it, you would, in order to make it accelerate just the same amount, you would have to put more force into it, right? So the amount of force that you need to make this ball accelerate depends on the mass of the ball and how far you want it to go. So if you want it to go really far, you are going to have to apply a lot of force to it, the heavier that the football is. And so Tom Brady, he is our new quarterback for the Bucs one of these days when football starts back up again. So what do you guys think about that? I assume you're pretty excited about that maybe. And so he is going to be, sorry, I just lost my train of thought on that. Okay, anyway, yes, so he's our quarterback. So that is exciting. If you, so sorry, I lost it. Oh, I know what I was going to say, is that years ago they had threatened or said allegedly that Tom Brady was using a football that was filled with helium instead of air. And of course, helium is lighter than air, so that would make the football have less mass. And therefore, allegedly, if it was kicked with the same amount of force, but it had less mass, it would accelerate more, and then that would be cheating. Mythbusters did a episode on that and found actually that to be a myth. But anyway, just thought I would mention that. Okay, so now we have third law, and in Newton's third law, you are looking at the action and reaction forces. So when a football player collides with another football player, then they're both exerting a force on one another. According to Newton's third law, the force that is exerted on both of those players is exactly the same. And the difference is going to be the mass of the players. So you've got your big football players playing, you know, the positions. Oh gosh, I need to know more about football. You've got your bigger players that are going to be doing your tackling because they have more mass. So they are going to be striking with more, with equal force, but because they have more mass than maybe another player, the player or the ball is going to go in the direction of the most mass. So anyway, The video will do a better job at explaining that, I hope. Okay, here we go. So you're looking at question 7, 8, and 9 on the worksheet, the last 3. Oops, that is still the old one. Oh no, I think I just made a big boo-boo. Oh, I did. Okay. I just lost my, I closed out the whole internet by accident. Okay, well, we're going to get that right back up. Pardon me. Okay, hopefully. Oh no. Okay, we'll get these back up here.
Threw me off track. So it's kind of
Apologize.
Whether it's a running back breaking through the secondary or a wide receiver on a foot race for the end zone, most defensive players in the NFL have a single goal in mind: to get downfield as far and as fast as possible.
we're thinking, wow, I've got to get from A to B within a certain time frame, and I can't let this guy throw me off track. So it's kind of like a chess match at that point in time. It's the battle to see who's the toughest.
Defenders, on the other hand, have a different.
Oh my gosh.
You can't see the video.
Okay. I understand. Okay, is this the one? Yes, okay. All right, so sorry about that. I hit a wrong button and that kind of messed me up. Okay, you can't see the video yet. Where are my peeps? Okay, here you guys are. All right, so let's try that again. Okay, all right, here we go.
Whether it's a lineman stuffing a running back or a safety colliding with a wide receiver, all NFL defenders have a single-minded goal: to stop the ball carrier.
The object of making a tackle is you want to get the guy down and limit the amount of yards he's able to gain, especially after contact.
When a tackle is performed correctly, it's not just a thing of defensive beauty. It's also an elegant depiction of Newton's third law of motion, sometimes called the action-reaction law.
All right, guys, that was your answer to number 7. Another name for Newton's third law is action-reaction law. You can see the little closed captions down here.
Newton's third law says that each action or force has an equal and opposite reaction. So if I were to push against a body, that body is going to push back against me with an equal and opposite force.
An important part of Newton's third law is the concept of momentum, which in football is the mass of a player multiplied by his velocity, represented by the formula P equals mv.
There you go. There is your equation for momentum. We learned this on Wednesday in our notes also. And I pointed out the fact that it's kind of weird that momentum symbol is a capital P. I am not exactly sure why, other than the fact that M is already taken by mass. And so they use P equals M times V. M for mass, V for velocity.
NFL players may not know the formula, but they're keenly aware of the role momentum plays in tackling.
It's very important to have some speed and momentum as you're going in to make that tackle. The better you're able to use that to your advantage, the better you're able to make contact and get a guy down right away.
In every collision on the football field, Newton's third law dictates that the total momentum between players must be the same before the collision as it is after the collision. This relationship is referred to as conservation of momentum.
The law of conservation momentum says that the P, the momentum before the collision, is equal to P, the momentum after the collision.
This law, represented by the formula P before equals P after, can be illustrated with a simple toy called a Newton's cradle.
In this case, we have displaced an initial sphere, and when we let it go, it has some momentum. It's mass times velocity. When it impacts the next sphere, that momentum is transferred through the middle three spheres and then passed on to the final sphere. And so because it has the same mass, it will move away with the same velocity that the first sphere impacted the middle three spheres.
The interaction of balls on a Newton's cradle can help illustrate what's known as an elastic collision, defined as one in which there is no loss of kinetic energy in the form of heat, sound waves, or deformation of the object. On the football field, collisions are typically inelastic collisions because kinetic energy is released, mostly in the form of compression between the players' bodies and sound waves.
Inelastic collisions are the rule of the day. We see them all the time in football. That is the energy of motion of two runners. After they collide, that energy is dissipated in deforming their bodies. That's like a spring. So some of your energy of motion went into that compression. You might have heard a loud snap from our pads. Some of the energy of our collision was transferred to the energy in the air that you hear.
While big hits look and sound spectacular, what's most important in tackling is stopping the ball carrier's forward progress.
If your pads are underneath his and you're hitting on an upward slope, you direct the energy up and you take him back. At the point of contact, hopefully that's where the ball stops play in.
Whether a tackle is successful or not, we can be certain that the same force is exerted on both players, and the total momentum before and after the collision is the same. For that, we have Newton's third law to thank.
So, did we, when the momentum, all right, so I'm sorry, when the players are colliding with one another, is the total momentum the same before the collision as after the collision? That was our very last question on the worksheet, and I said it at the very end. Who can tell me, is this a yes or a no? I see people writing on the chat. Yes, that's right. The collision or the momentum is conserved. So it's kind of like Newton's cradle. So I've got my Newton's cradle right here, trying to see if you'll be able to see it. Maybe that's a little bit better. Okay, so with Newton's cradle, it's a good example of this conservation of momentum and Newton's third law. So when I move the ball, the first ball out, it will collide with the other ball. And notice that it is sort of slowing down right now. When I ordered this, I thought it was gonna be so much bigger. My other ones were damaged. And okay, so notice that it doesn't keep going forever and ever, but as one ball hits the other ball, it transfers its energy, energy of motion or force of motion, remember, which is momentum. It transfers its momentum to the next ball, which transfers it to the next, and so forth, which made this last ball come out. Now, this is an example of close to an elastic collision because almost all of the energy is transferred, but not all of it. If you listen carefully, you can actually hear sound. Let me do this here. You can hear sound. So some of the energy is going off as sound, and it would be a small amount, but there is some temperature change too, some giving off as heat as the collisions happen. And so eventually it does kind of slow down. And Asher's raising his hand. Okay, Asher, how can I help you? Let's see if I can.
Um, a couple of us are confused on what number 9 is. How many people got number 9?
Okay, so Asher, if you could mute yourself again. Yeah, let me mute you there. Good, thanks, because we were echoing. So yes, so when two players collide, the momentum is conserved, and basically what is happening now, it's an inelastic collision because there is going to be some energy that's going to be dissipated as heat and sound. You'll probably hear some of the cracking, but basically what Newton's law, third law, is saying is that when two objects collide or are pushing on one another, let's say that astronaut and this football are colliding. The astronaut is going to be pushing on the football with a certain amount of force, and the football is pushing back on the astronaut with the same amount of force, even though one may be bigger. So we're going to assume that the astronaut has more mass than the football, and therefore, if they were both colliding on one another, they would be exerting the same amount of force on each other, but where the football would go, would the football keep on traveling or would the astronaut be stopping the football, is going to depend on the mass. So the object with most mass is going to send that object in the direction of their force. So the astronaut would be sending the football, this way if they collided to one another, because the astronaut's going that way. So, and then we're going to learn more about all three of these laws. But looking at all three laws from Newton's standpoint, from football standpoint, with the first law, law of inertia, an object wants to keep on moving in a straight path at a constant speed unless an unbalanced force acts on it. And that includes if the object is at rest. So if it's at rest, it doesn't want to move from rest. The only way an object can change what it's doing, change its movement, change its velocity, which means it could either speed up, slow down, or change direction. So the only way that can happen, though, is if an unbalanced force is applied to it. So an unbalanced force would be what would be required for this football to, go into the goalpost. So in order to make that happen, an unbalanced force has to be delivered, and how much force is going to determine on the mass of the object that the force is being applied to, and how far you want it to go, so how much you want it to accelerate. So if the object was heavier, you were throwing a bowling ball instead of a football, you would have to apply more force to make it accelerate the same amount. Or if you didn't, you applied the same amount of force to a bowling ball, it would not accelerate as much. So it's that whole relationship between force, mass, and acceleration of the object. Newton's third law then states that when two objects collide, the action force is equal to the reaction force. This is the most commonly misunderstood law of the three. And it's going to take some practice that we're going to be delivering a lot of over the next couple of weeks, because we're going to be practicing with these laws pretty much till the end now. This is where we're at, and then we're just going to have some fun with them. And each step along the way, you are going to need to be sorry, I got distracted again. Each step along the way, you're going to need to be able to explain these laws. So the third law, we're going to have to take some time on. Understand that, like, say, again, in the example of the astronaut and the football colliding with one another, they're exerting a same force on each other. That's the equal part of, for every action, there's an equal and opposite reaction. The equal is equal in strength. So the force that the astronaut is putting on the football and the force the football is putting on the astronaut are the same. Like that number, 10 newtons, let's say, would be the same. But the opposite part is opposite direction. Football's going, to the left, astronauts going to the right. And so that's the opposite. Football pushes the astronaut pushes back on the football with the same amount of force in the opposite direction. So lots of practice on that, and I have some fun challenges. So please make sure that you check EdSP for the materials list for the next couple of weeks. There will be things that you might have access to and things that you won't. Like, for example, hula hoops and balls, different size balls, and pennies, and glassware, and tablecloth. So there's various things, and you may or may not have all of these materials, and that's okay. We'll improvise where we can, and if you don't have access to them, you'll have access to me, and I'll be doing them for you. And then we're going to have some challenges for the Olympics at the end of the year, which isn't that far off, actually. So is there anybody that has any questions on today's assignment? This is due, by the way, on Monday. Yeah, Monday by 11 o'clock. Starting next week, we're going to have things due on particular days. It'll be a little bit more streamlined, but anyway, this is due on Monday because that's what I told you at the beginning of the week. So I'm not going to change it on you. There's a submit box for it already. Asher, how can I help? Or your hand might actually still be up, Asher, from last question, maybe. Anybody else have any questions? No? Okay. All right. We ended just a little bit earlier, and which I kind of wanted to do because the Wednesday I kind of started to go into my IPS class time a little bit. So I have another class in a few minutes. All right. Well, I think that you guys maybe learned a little bit more about Newton's laws. Some of you were interested in the football, some of you maybe not. But if you weren't, don't worry. We're going to have lots of examples using lots of other types of sports and other funky ways of moving to learn about Newton's laws. Okay. Have a great day, guys. See you. Oh, yes, Bryson. How can I help?
What was number 9 again?
The answer was yes.
Okay.
The total momentum was conserved.
Okay.
Yeah.
Thank you.
You're welcome. Anyone else? Okay, so if you guys are good, I am not actually signing out yet. I'm going to be admitting some people from my waiting room that's an IPS to tell them that they have to sign out and come back in. So those of you that have been here, like Derek, Andrew, Mason, I think you're still with us. Is there anything I can do to help you guys? Or if not, you guys can head on out and enjoy the rest of your Friday. Okay. All right. Bye, guys. Hey. Hello, guys. I am admitting you because I didn't want to have a reboot of what happened on Wednesday. But hi, guys. Happy Friday. I'm glad you're here. So this is technically still my comp science class. I have gotten, I have dismissed them all. And so the few people that are in here right now, there's 7 of you. Let's see. Hi, Eli. Hi, Alex. Hi, Henry. Hi, Liam. And hi, Libby and Zane. Really glad you could join us. But here's the deal. So because I use the same code for both of my classes and they're back to back, I kind of need to end this one. Oh, I think I might even, I'm still recording.